We've already talked about the general log rule in terms of its equations, the logarithmic equation and the associated exponential equation, and vice versa. Now we want to relate that to the graphs of the standard logarithmic function and the standard exponential function and discuss how these functions are actually inverses of one another. So if we have the equation, and we'll write it over here, log base a of the argument y is equal to x, we know that the graph of the standard log function looks something like this. So we have a vertical asymptote at x equals 0, and the function follows the y-axis up from negative infinity here, up the y-axis, and then comes and levels out over here as x gets large. Remember that the associated exponential function that relates to this logarithmic function is the exponential a to the x is equal to y, and the graph of this exponential function looks like this here. It crosses the y-axis at 0, 1, the point 0, 1. It has a horizontal asymptote at y equals 0. In other words, the horizontal asymptote is the x-axis, and it skims along the x-axis here and then eventually comes and scoops upward. The key here is that these two functions are inverses of one another, which means that they are reflected over the line y equals x. So this line here, this diagonal line, is y equals x, and you see the logarithmic function down here and the exponential function up here. These functions are inverses of one another because their graphs are mirror reflections of each other over the line y equals x. Remember that inverse functions have their x and y values reversed. So for instance, if I look at a point here on the logarithmic function, I have this point right here. That's the point 1, 0. If I reverse these x and y values, I get the point 0, 1. And if I go plot the point 0, 1, I get 0, 1 is this point right here. I find that that point, 0, 1, happens to be on the graph of the other function. If I look for another point, I can see this point right here is approximately, let's say, 4.5, so that would be 9/2, and let's see, 1.5, so about 3/2, approximately. And this point doesn't necessarily satisfy the logarithmic function, it just looks like it's approximately on the function. So let's pretend that it is for a second, that we have that point 9/2, 3/2. I would expect that the inverse function of this log function, whatever it is, should satisfy the point 3/2, 9/2, the point I get when I flip these two values. So instead of 9/2, 3/2, I get 3/2, 9/2. So if I go find 3/2 and then 9/2 up here, I see that I wind up right at this point right here. That is 3/2, 9/2. And so what I can see is that these two graphs represent functions that are inverses of one another because no matter which point I pick, if I flip the values in the coordinate point, I end up with a point that is along the other graph. So what we want to understand, what we want to take away from this, is that the general log rule that allows us to convert from this logarithmic form to this exponential form and vice versa, when we do that, we're changing the expression into its inverse function. So if we started with this log function and we use the general log rule to convert to this exponential function, we're finding the inverse. We're finding the graph that's going to be reflected over the line y equals x, and knowing that can help us solve different kinds of log problems. For instance, we can even be given, instead of the graph of one of these functions, a point set. So for instance, we might be told that we have the point set x and then y equals a to the x. And maybe we have the set of points 1, 2, 3 for values of x, 2, 4, 8 for values of y equals a to the x. This y equals a to the x function here is the exponential form here, a to the x equals y. So what we're saying is when we go out to x equals 1, the exponential function is going to give us back a value of 2. When we go out to x equals 2, the associated value for y is 4. We're also going to have the coordinate point 3, 8. So if we were to plot these 3 points, let's just go ahead and borrow one of the coordinate axes we have here. So if we plot the point 1, 2, we come out to 1 and then 2 here. If we plot the point 2, 4, we get 2 and then 4 here. And if we plot the point 3, 8, that's going to be 3 and then all the way up to about here. And we can see that that's the exponential function coming together. So if we try to connect these roughly as an exponential function, it might look something like this. Okay, so let's say that that's our exponential function graph. And what we're asked to do is find a set of points that satisfy the associated logarithmic function and to sketch its graph. All we have to do is come up with the reverse point set. Instead of 1, 2, 3 up here for x, we say 1, 2, 3. And instead of 2, 4, 8 on the bottom, we say 2, 4, 8. Then here we have the point 2, 1. So we have the point 2 and then 1. Here we have the point 4, 2. So we come out to 4 and then up to 2. And then here we have the point 8, 3. So about up to here, and 3 is about right there. And if we connect those in a curve, that might look something like this as a logarithmic function. And this is a rough sketch, but what we can see here is that we have two functions, one exponential, one logarithmic function, that look like they are reflected roughly over the line y equals x. So we see that we have these points here that are roughly equidistant from the line y equals x. They are a perfect mirror reflection of each other over this line y equals x. So for problems like that, when you're given this point set and you want to graph the inverse function or the associated exponential or logarithmic function, just the other version, we just have to flip the points around, flip around the coordinate points, and then sketch both versions of the graph. If we've done it right, they should be mirror images of one another over this line y equals x.